In this chapter, we describe speed control, current detection, and position detection. To reach the target speed from the actual speed, PI control is performed to calculate current command values, IQ_ref and ID_ref. Since position detection is unstable during startup, the actual speed measurement, omega, is not accurate. Therefore, the current command values are not calculated based on the results of PI control. Instead, they are derived from the predefined current values necessary to start a motor. In current control, output voltages for the magnetic field component, Vd, and the torque component, Vq, are determined based on the deviation between and the actual current, Id, of the magnetic component, and the target current, ID_ref, of the magnetic component, and the actual current, Iq, of the torque component, and the target current of the torque component. PI control is one of the methods used. We describe a three-phase PWM output. PWM signals are produced based on the set points of Vu, Vv, and Vw, to control the inverter circuit. For vector control, it is necessary to measure a current flowing through a motor. There are three detection methods: three-shunt method, one-shunt method, and two-sensor method. In current detection, currents in U phase, V phase, and W phase are measured. The normalized values are the current values of each phase, IU, IV, and IW. We describe position detection. In sensorless control, a rotor position is estimated using the amounts of current of the magnetic field component, ID, and the torque component, IQ. And the speed, omega, and the rotor angle, theta, are calculated. Back EMF voltage is used in calculation to determine whether the obtained speed, omega, and rotor angle, theta, have reached the estimated values. First, back EMF voltage, E, is decomposed into a torque component, Q, and a magnetic component, D. Since the target speed is not normally equal to the current speed, back EMF, E, resides on the Q-axis, off the Q-axis. Consequently, back EMF, ED, is induced on the D-axis. PI control is performed in such a manner as to make ED 0. Speed, omega, is estimated using equation 8 and equation 9. Since the unit of measure of speed is revolutions per second, the estimated speed is multiplied by the control cycle period. The result is added to the previously estimated position to estimate the rotor angle, theta, using equation 10. That concludes the description of vector control. Finally, we describe the vector engine incorporated in Toshiba microcontrollers for vector control. The vector engine is a coprocessor that is independent from the CPU and performs coordinate transformation calculation and PI control for current control. The vector engine, motor control circuit, and AD converter are built in hardware working in an interlocked fashion without software processing. Thus, a CPU utilization rate can be greatly reduced, and it realizes performance higher than that of its operation clock. In addition, software development is not needed for complicated vector transformation calculation. Therefore, the development load can be reduced. For more information on the vector engine, please visit our website.